then I can record. All right, fantastic. So we are talking about chemistry of the troposphere today, and that's where we are. So this is obviously really important. We talked a little bit about the stratosphere on Tuesday. So we're going a little bit lower, closer to where we exist, and the things that affect us. So we're going to talk about like pollution and greenhouse gases and stuff like that too. So, of course, I don't even have this plugged in. Thought I was ready. Chemistry of the troposphere. So there's a whole lot of pollutants in the troposphere. You guys probably know that. We're not in like a super big city where we have a lot of smog or anything like that, but smog is definitely a problem in large cities. And we're going to talk about what that comes from and stuff today. So there are pollutants that are basically because of human activity. And I would call those unnatural pollutants. These are ones that are due to human activity. And that's like, it's usually excess of the stuff. So like we've made too much excess SO2, carbon dioxide should be something that you're familiar with, carbon monoxide, nitrogen monoxide, and extra ozone, which actually might surprise you a little bit. So these are all unnatural pollutants. Now, some of them can be made naturally, but we've kind of made an excess of most of these here. Sorry, I just wanted to zoom in a little bit, of most of these compounds. I'm going to talk about what they do to our environment today. So the first thing I'm going to talk about is sulfur and acid rain. I know you've all heard about acid rain. Obviously, acid rain is rain that is acidic, which can cause all kinds of problems. Now, acid rain would occur naturally and does occur naturally. We just kind of compound it with all the stuff that we do. So the natural sources of acid rain are sulfur from volcanoes. And you might think, well, volcanoes don't erupt all that often, but when they do, they release a lot of sulfur into the troposphere. So that's where a lot of natural sulfur and sulfuric acid and stuff comes from. It can also come from things like forest fires, and we're going to talk a little bit about what those release as well. So the main natural source of sulfur is from volcanoes. So we shouldn't have a ton in the atmosphere, but we, of course, combust just about everything we can find, and that also releases sulfur. So unnatural sources are us doing combustion of coal and oil. Now, not all coal and oil has a bunch of sulfur in it. If it's from different parts of the world, it might have more or less sulfur in it. And we've kind of tried to find some ways to remove that sulfur because when you burn it, the sulfur turns into sulfur dioxide in the atmosphere. So sulfur dioxide is really what causes the problems when you actually burn the sulfur. So I'm not actually going to write out the full chemical reactions that happen, but essentially when you have sulfur that gets combusted and turned into SO2, okay, that happens in volcanoes, it happens when we combust things, it happens in forest fires. That SO2 is going to react with oxygen in the air and oxidize into SO3. Okay, so how does this happen? This little arrow right here was oxidation in the air. And once it turns into SO3, then it's going to mix with water. Okay, mix with water, aka acid rain, right? And it turns into sulfuric acid. Okay, so sulfur dioxide is oxidized with oxygen, and then it mixes with water and we get sulfuric acid. So that's how we get acid rain. So if you're looking over at this picture, a lot of the pollutants, and we're going to talk about NO2 and CO2 also, but we're right now focusing on SO2. When it gets produced, of course, it goes upwards and it gets into the clouds. And then once it comes back down, that's how we get acid rain, which of course can destroy all kinds of plant life. So natural rain actually is a little bit acidic. Natural rain has a pH of about 5.5. Okay, there's a reason for that. It's about 5.5 because it does have carbonic acid in it. So where that comes from is CO2. So we know CO2 is a prevalent part of our atmosphere. CO2, when it's with water, turns into carbonic acid. So naturally, because of the CO2 in the air, rain is about a pH of 5.5. Now, when we start introducing sulfuric acid, that shouldn't be there. However, acid rain has a pH of about 4.0 or lower. And that's where our problems come from. So a pH of 1.5 might not seem like a lot, but that's like 150 times the amount of acid that it should have in it. So it does make a big difference, okay? So natural rain versus acid rain. So over time, of course, this affects the groundwater and the lakes and rivers and things like that. This one's from 2010. This was actually the most recent map like this that I could find. And you might not be able to see it very well if you printed it in black and white, but it's been a very common and consistent trend that the east side of the US is a lot more acidic than the west side, and that's just because of population density, right? We burn a lot more coal and oil over here than we do over here because of the people that exist. But if you're looking at the colors, there's some like red spots where some big cities are, and that says that's a pH of less than 4.1. So that for lakes and rivers and things is very acidic, because if you look at this pH levels for aquatic organisms, snails like to live at a pH of 6, clams are at 6, a lot of fish are at like 5.5. You start getting lower than that, they all start to die. Frogs can exist at a pH of 4. You go any lower and then even the frogs are gonna die. And then actually anything under 4, microorganisms can't exist under that. So microorganisms can't survive. And so some of these areas that are at like 4 point, let's see if I can find one. There's some like 4.8, 4.7. Yeah, that's probably the lowest one I can see. That's pretty tiny. But if it's at like 4.7, then the only things that are going to exist are perch, frogs, and those microorganisms. If we get too acidic, everything's going to die, because of course, if we don't have microorganisms, that's going to screw up the entire food chain. So acid rain over time can definitely be a problem. So we have started trying to combat that, and I'll talk about what we did in a second. So of course, acid rain over time lowers the pH of lakes, rivers, etc. Okay. Now, not only does it affect these organisms, it also destroys buildings. So any buildings that are made of stone and metal will react with that sulfuric acid in the acid rain, okay? And then they start to degrade. This very commonly starts breaking down historic buildings, and there's a reason for that. So historic buildings are most affected. Excuse me. That's supposed to be an A. Okay. So historic buildings are actually affected a lot because they are generally made of stone or limestone. So historic buildings are made of limestone. Limestone is just calcium carbonate, and this reacts very readily with acids, or specifically sulfuric acid. Excuse me. So that starts to break down those buildings. Now, this specific reaction we actually started utilizing to try to fix the problem. So what we've done, I should have made a little thing for that. What we've done is we've tried to take out the sulfur from like the coal and oil before we burn it by using limestone. So we try to remove the sulfur. Hey, guys, in there, shoot, in there, go away. Okay, remove sulfur before burning by reacting with calcium carbonates. And so we can kind of control that. Guys, out. I am in the middle of class. Go away. I am so sorry. Go in there. You can play in there or upstairs. Shoot. Okay, so we kind of like utilize that reaction to kind of trap the sulfur before it gets burned into SO2. So that's kind of where sulfur comes into play. Notice when I was up here, I said something about NO2 and CO2. So I'm also going to talk about those here in a little bit. So before we do that, we are going to switch to carbon monoxide. So carbon monoxide is another issue in the atmosphere, and carbon monoxide is from incomplete combustion of hydrocarbons. So like we combust hydrocarbons in order to get fuel. The CO is a byproduct of that from incomplete combustion. incomplete combustion of hydrocarbons. Okay, an incomplete combustion, it just means that there's products other than water and carbon dioxide, because we always make water and carbon dioxide. It just means that there are other products besides CO2 and H2O. So like you can have some side reactions, you can have some of those breaking down when they interact with each other, but a lot of the times we make some carbon monoxide. So this is what happens if you run your car in your garage with the garage door closed, you get a lot of carbon monoxide, which is a problem because that can kill you. So CO obviously is bad for humans. We have carbon monoxide detectors in our house for this very reason. And I'm going to kind of talk about the reason why. So this is the Lewis dot structure for carbon monoxide. Okay, this is a triple bond, and we talked about how triple bonds are pretty stable and unreactive, and that's true. So this is fairly unreactive, but, and this is a huge but, these little electrons right here like to bond to stuff. Okay, so what they do, these like to bond to heme. This is heme, and that's in your blood, like hemoglobin. Okay, so what happens is, so this is a heme molecule. See the little iron there? So we've got iron in our blood. Oxygen is supposed to bond to heme. However, if there's too much carbon monoxide takes the place of the oxygen and your body can't circulate oxygen. So the problem is that heme has an affinity for carbon monoxide 210 times greater than oxygen. So if carbon monoxide is really abundant, it's going to attach to the heme instead of oxygen, and that's where those problems come in. So that's what will kill you, is essentially your blood not being able to circulate oxygen because it's circulating carbon monoxide instead. So that's essentially what will kill you. So you need to be really careful and keep your carbon monoxide detectors up to date. Okay. Now, if you are a smoker, which I highly do not recommend ever, but smoking and carbon monoxide, this is kind of part of the reason that smokers can't breathe as well. You might be coughing a lot. You can't circulate, your body doesn't circulate oxygen as well. And part of that reason is because what's going on is incomplete combustion and you're making carbon monoxide. So a non-smoker usually has 0.3 to 0.5 of these, this HB stands for hemoglobin, with carbon monoxides on it. Whereas a smoker usually has up to 4% of their hemoglobins have carbon monoxides on them. That's what that COHB stands for. So that's a really big difference. Okay, so the more carbon monoxide that you have attached to that heme means you have less oxygen attached to that heme. And over a long period of time, this can kill you. Okay, so if this is sustained, this high concentration is sustained over time, that can lead to death. Okay, so you don't want to obviously inhale a lot of carbon monoxide. All right, so that's carbon monoxide. We're going to move on to another pollutant in the atmosphere, and that is nitrogen oxides. And notice I didn't say like nitrogen monoxide or nitrogen dioxide. There's actually multiple molecules that are made of nitrogen and oxygen that are pollutants for us. So anything that's a nitrogen and oxygen compound. So I'm going to talk about smog, and I kind of mentioned this at the beginning of class. Smog doesn't necessarily affect us here in Bloomington Normal, but in larger cities, it can be a huge problem. It's a huge problem in China. It's like brown air. Okay, so smog is really made of brown compounds that are nitrogen oxide compounds. So these are brown compounds. And they're like N something, O something. Okay, there's multiple numbers. Now, usually the one that's brown and causes the air to go brown is nitrogen dioxide, but it can be NO, it can be N2O4. They all kind of exist in an equilibrium and cause a multitude of problems. So that's what smog is. Now, if we didn't have smog, so under normal conditions, we know most of our atmosphere is made of nitrogen and oxygen. So we're gonna look at this reaction really quick. If it were going to react and make NO, that would be considered a nitrogen oxide. This reaction has a K value of 10 to the negative 15th. Notice this is a very small K value. That means this reaction really does not go to the right much at all at 300 Kelvin. And 300 Kelvin is like a little bit warmer than where we normally are at. But in general, this reaction like doesn't happen much at all. Okay. Now, however, when we have things like electric discharge or in automobile engines, the nitrogen and oxygen, will you shoot? Go away, you can have it, go away. Nitrogen and oxygen, this reaction is much more likely to happen because I want you to look at this. The K value is now 0.05. Now, it's not completely going to the right, like, but it's definitely making a lot more products than if K was 10 to the negative 15. So this is a larger K value as the temperature goes up. So essentially, if it gets that hot, and it does get that hot in automobile engines or when lightning strikes, you're much more likely for this reaction to happen. So we're going to make this NO, which is a problem. Okay, so is that all I wanted to say about there? Yeah, increased temperature if it's hot enough. That's the only thing that I want to write there. So the hotter it is, the more likely this is to occur. So more automobile combustion, more nitric oxide being produced. So when we have a bunch of this NO in the air, it can cause problems, but it also can react on its own. So a reaction the nitrogen oxide does, or nitrogen monoxide does, is it'll react with O2. So this is another reaction that can happen. So 2NO can react with oxygen. And this is how we get all of this brown stuff, this 2NO2. Okay, this K value is 10 to the 12th, which is huge. And that's at 300 Kelvin. Like that's at a normal temperature. So this reaction, so if I have a whole bunch of this reaction is definitely going to happen and I'm going to make a bunch of NO2. Hey. Okay, so this reaction is very likely to happen. These are all based on your K values. So we have to understand what K value is in order to determine, guys, if a reaction is actually going to occur or not. Okay, hang on. Okay, so another reaction that can happen. So these are all possible reactions, right? So this is how we make NO. This is what NO does. We can also have photodissociation of NO2. So we talked about photodissociation on Tuesday. That's just like absorbing energy and breaking apart. Well, this can happen to NO2 as well. So NO2 can absorb some wavelength. And if that happens, it's going to break into nitric oxide and oxygen. Notice we already saw this guy, and that's pretty reactive. We can get a lot more NO2 back from that. But this should also kind of point out to you, we talked about little free oxygens on Tuesday and how they like to attach to O2s, and that's how we get ozone. So this actually makes more ozone. Now you might be like, well, that's a good thing, right? We want more ozone. Well, remember, we're in the troposphere. Ozone is supposed to be in the stratosphere. Okay, so if you look at this little graph here, the ozone layer, this is where we've got all of our ozone, and that's good. But if we go lower, we should not have that much ozone. But right now we kind of do have a decent amount of ozone, and that's because of this pollution that's going on.
Hello.
Hi.
Sorry I'm late. I was driving home from school. I wanted to leave before it got worse. So
that's fine. I'm recording this, so I'll post it later so you can go back if you need to.
Okay.
Okay. Great.
Got it.
Okay. So yeah, we're on page 6 of the ones that I posted online. So here are we. We got more ozone, which is great, but I was just talking about how ozone, when it's in the wrong spot in the troposphere instead of the stratosphere, it causes problems. Okay, so ozone as a pollutant. So this is true near the ground because it's so reactive. It's so reactive. So like ozone is great to protect us because it reacts with all those rays coming in from the sun, so that not as many of them get through. But we don't want all those reactions happening close to us because that's going to give off a lot of energy and it's going to break down oxygen that we need. So it's so reactive. So it's going to take up some of those O2s. And this really causes problems a lot of the time for people who have asthma and the elderly. So this causes problems for asthmatics and elderly. So if we don't have the right percentage of O2 in the air, we can't breathe very well. Joey, can you stop? I will watch it later. Stop. Okay, so NO making O3. We got problems with NO2, we got problems with NO, we got problems with ozone. But we kind of do have a fix for this. And you might know what this is. This is called a catalytic converter. You're required to have these in your car. And what they do is they convert these things that we don't want, these carbon monoxide, these hydrocarbons that are unreacted, these nitrogen oxides that we were just talking about, into things that are not so problematic. Now, CO2, yes, problematic, but it's better than carbon monoxide, and water and nitrogen. All of these things are pretty stable and normal for our atmosphere. So catalytic converters are hugely important in reducing things like smog. Okay, so these ones are much less problematic. Okay, and these reactions where it's like breaking them down are very important. Okay, so catalytic converters, huge help for reducing smog and pollutants in the atmosphere. Okay, so now I'm going to talk about greenhouse gases. So this is like a much more controversial and big topic, especially right now. So I really like talking about these, and you might have questions. You might want to chat with me at some point. It's really interesting how greenhouse gases affect all of this. So it's a delicate balance in our atmosphere. And we're going to talk about all the molecules that kind of affect this whole global warming or global climate change, whichever you would like to call it, and what's really going on. So